All right, everyone, and welcome to my whiteboard, I guess. At the end of the video, I'll show you the ridiculous contraption that I'm using in order to capture this, but hopefully you'll be able to read what I'm doing here. So let's just recapture what we did last Friday. We had 2 point masses on the end of a 1 meter long stick. And so that was 1 meter. And we had that going around in a circle about the axis. I'm going to use a triangle for the axis. So there's the velocity of that thing. There's the velocity of that thing. We'll call that mass 1. We'll call that mass 2, velocity of mass 1, velocity of mass 2. Those are tangential velocities. Now, that's a meter stick. So our radius here, R1. Here's our radius, R2. We know those are both half a meter. And what I asked was, what was the kinetic energy of the system? We figured out that that was just the kinetic energy of the parts of the system. So since the system consisted only of 2 masses, there you go. And so here's what we had. We had 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Now, over here, we remembered that if this thing had a rotational rate of omega, remember that omega is the same for every single mass or point on the object. We pretended this stick was massless for now, but we knew that this was equal to the ratio of the tangential velocity of the point to the radius of that point from the axis of rotation. It's so important that r in this is always from the axis. Now, we're going to have a little bit clearer of a notion of that a little bit later about not just from the axis, but it's going to be the shortest distance from the axis to the point in question. So shortest distance of a point from a line, yep, that's another line that's perpendicular to the axis. But hold on to that. Therefore, we could say that v of 1 would be omega r1. Once again, we don't need a subscript for omega because the omega is the same for every point on a rigid rotating object. And so we come back here, 1/2 mass 1 omega squared r1 squared plus 1/2 m2 omega squared r2 squared. And then we factored out the common terms. So we factored out the 1/2, we factored out the omega squared. And then we were left with this term in the middle, m1 r1 squared plus m2 r2 squared. Now if we look at this, this is a nice expression. Here's why. 1/2 m1 v1 squared, well, that term can just deal with any one point on the object. But the nice thing here is omega describes a rigid rotating object holistically. So that's a really great thing. So if this term here could describe something holistically for the rigid rotating object, that would be great. And that's where we're going to come out to 1/2, and then I'm going to define that term as I omega squared. So if you look at this 1/2 mv squared, the parallels become a little more clear. 1/2, 1/2, whatever. Omega squared v, and this here is v com squared. And then this term here occupies the space of the mass in the translational kinetic energy term. So this must be something about inertia, but in a rotational sense. And that's where our moment of inertia is. So we're going to define I for a series of point masses to be equal to the sum of the mr squareds. Now I could do the proper notation here with, the sub I to k and whatnot, but let's just leave it at that, right? And so all we're going to do is add up this contribution from each of the points, and that's what we're going to be looking at. So a couple of things about that. Here we go. Let's do a sample problem. And we'll do a nice simple sample problem, or so will seem. Or rather, I'm going to start the sample problem, and y'all are going to work on it and finish it. So let's say I had 4 masses that were arranged in a rectangle. And just so that our masses are kept in a rigid orientation with respect to each other, we're going to connect them with infinitely thin, massless rods. Now, I know they don't exist, but well, just roll with it. Here we go. We're going to say that this distance here is 4 meters. We're going to say this distance here is 2 meters. We're going to call this mass 1, mass 2, mass 3, and mass 4. Over here, let's say that mass 1 is equal to 3 kilograms. Mass 2 is also equal to 3 kilograms. Mass 3 is equal to, why don't we make that, I don't know, 9 kilograms. And mass 4 is also equal to 9 kilograms. Okay, now I could have just chosen things fairly randomly there, and I kind of did, but we'll see some reasons why I chose those numbers just for sake of ease maybe later. So here's the thing, I have this rigid rotating object. If I ever asked you what's the moment of inertia of this system, you should just stare at me and go, well, I can't answer that question. Well, why? Because we need to always specify an axis of rotation. So I'm going to do this problem about a couple of different axes, and then I'm going to set you a bunch of different axes to try by yourself, and then we'll check it, and then tomorrow we're going to look for some patterns. So the first axis that I'm going to choose is an axis that bisects the system vertically. We're going to call that axis A. The second axis is going to be an axis that bisects the system horizontally. I'm going to call that axis B. So that would be if it's this, that would be rotating the system like this around that axis. B would be this way. And then a third axis that I'm going to pick is through the page like this, such that the system would rotate like that. I don't want to ruin my system here, so there we go. And that's going to be C. So I'm going to do those 3 axes first, and then we'll take a look. And then we'll look at some other axes. So IA. IA is going to be the sum of the MR squareds. And so what does that look like? Well, if I was going to do this formally, which I'll do the first time, it'd be M1R1 squared plus M2R2 squared plus M3R3 squared plus M4R4 squared. So here we go. Mass 1, 3 kilograms. How far is mass 1 from axis A? It is 1 meter squared. Plus M2, 3 kilograms times 1 meter squared. Plus 3, that's this one here, 9 kilograms times, once again, 1 meter squared. Oh, this one's nice and simple. Plus, and we can see that this one is 9 kilograms times 1 meter squared. And next time I'm not going to write all this out, I'm just going to plug in the values. So what do we got here? We have 3 apparently kilogram meters squareds plus 3 kilogram meters squared plus 9 kilogram meters squared plus 9 kilogram meters squared, and altogether that is going to equal 9 plus 9, 18, plus this, 24 kilogram meters squared. Now that number is not going to mean anything to you in and of now, but when we have a bunch of them, we can look at that comparatively. So I'm going to go to a fresh sheet of paper. We're going to look at IB and IC. You can use, we'll come back to this sheet of paper to look at some geometry. So here we go. IB is equal to, well, I'm just going to start by filling in a quick pattern, since we know that that's going to be the pattern for every single one of these. Right? And so now it's just a matter of filling in the pattern. So if you notice here, going back, well, what's the R for B? Well, it is the shortest distance, boom. And if you can think about that, that's actually the radius of the circle this thing will travel around as it goes. So what's that going to be? That's going to be 2 meters, 2 meters, 2 meters, 2 meters. So if we look at this then, I'll just drop some units in the intermediary step. This is going to be 12 plus 12 plus 36 plus 36 equals 36 and 36 is 72, 72 and 24, 96 kilogram meter squared. So then comparatively, we would say that it is more difficult to rotate this thing about axis B than it is around axis A, which should make sense because more of the mass is further from the axis. So now let's look at IC. Okay, So here, what are our r's going to be? Well, our r's are going to be this distance here, because if this is my axis, the shortest distance from here to 1 is going to be this line here, which is half the diagonal, right? Or if we look at this, it's going to be 1 meter squared plus 2 meters squared, and I'll show that in just a second. So 3 kilograms squared plus 3 kilograms squared plus 9 kilograms, whatever that is, squared plus 9 kilograms, whatever that is, squared. So we said that each of these terms is going to be the square root of 1 meter squared plus 2 meters squared, right? I'm just going to put some ditto marks in here, right? So the square root of 5, or rad 5 squared, or 5, which is nice and simple then, because this becomes 15, right? Plus 15 plus 15 plus 15. Oh no, sorry, these are not 15. 5, these are 45 and 45. Oof, that was almost terrible. And so if we look at that, then we have 120 kilogram meters squared. Now, you'll notice that that's a lot larger than IB and IC. But does anyone notice anything else? Well, hopefully what you noticed is that if I take IA and I add it to IB, I get IC. What? Well, if we look back at here, interestingly enough, we have all 3 of these axes going through the same point. And it's a point that's in the plane of the figure. And so what we're going to learn here is our first interesting rule, something that's called the perpendicular axis theorem. And the perpendicular axis theorem is that when I have 3 axes that all go through the same point, that the sum of 2 of them is the third. But the sum of which 2? Notice that axis A and B are in the plane of the figure, and C is perpendicular to that figure. And that's the way it's going to go. So we're going to say the axis that is perpendicular to the plane is equal to the sum of the moments of inertia that are through the plane, assuming, this of course assumes the figure is in the XY plane. So, like I said, this is called the perpendicular axis theorem, right? So now, let me set you some problem to do. It's not out of the textbook, it's right out of here. I'm going to create a couple new axes, and I want you to find the moments of inertia about those axes. So let's go back to our picture. Here we go. Axis D, right? Let's have axis E be this one here. Axis F is through the page at that point. Why don't we have axis G being through 2? And then let's do one more. Normally what we would do here, folks, is I would have an axis for each member of class, and then we would get together and then pool our logic. Really don't have the freedom to do that here. Let's make axis GH. We'll make axis H outside of the figure, just so you don't think the axis has to go through the figure. So it's a vertical axis, and we'll say that this is 1 meter from here, and it's like that. And so I'd like you to find the moments of inertia for axes D, E, F, H, and G. And then I will post a solution set to that. And then tomorrow, what we're going to do is look at some comparisons with all of this stuff to see if we can see some new patterns. Okay, take care.